Welcome to problem 1. This is a mesh analysis problem that can be solved using Kirchoff's voltage law. This is part of a larger video series of basic circuit analysis. So this is our problem here. We have a 10-volt DC source on the left, labeled V1, and a 5-volt DC source at the top, labeled V2, and there are 5 resistors in the circuit. So the first step is to draw the loop currents in each mesh section. I've started on the mesh on the left, just above the DC source. So what I like to do is I enter a resistor, I put a plus sign. As I exit a resistor, I put a minus sign. And I usually like to go clockwise as my mesh current orientation. So you don't have to do this. In fact, you can reverse this. You can go counterclockwise if you want, and you can reverse the polarity if you want. But whatever you do, decide, just remain consistent through your entire circuit analysis. Otherwise, it's very easy to mess things up. So here I'm continuing on the mesh on the right with the mesh current for loop 2. Once again, as I encounter R1, I have a plus. As I exit, it's a minus. Now R3 is a little peculiar. If you notice, it's got 2 polarities, so this will always be with respect to the mesh current that you're looking at, what the polarity is going to be for that particular component. So that becomes exceedingly important when you start writing out the loop equations, which we'll do now. So starting with loop 1, we encounter the 10-volt DC source at the bottom. I'm going clockwise. I just started just beneath the 10-volt DC source, and the first thing I run into is a minus sign, so we get minus 10. Continuing clockwise, I run into R4. We hit a plus sign, so it's going to be plus R4 times I1. And then we hit R3. R3 is going to be I1 minus I2. Now, the reason that is because from the perspective of loop 1, which is what we're doing right now, the voltage drop across R3 is going to be I1 minus I2. And the loop current in I1 is going clockwise. The loop current in I2 also goes through R3, but it's in the opposite direction. So that's why we have I1 minus I2. We do the same process for loop 2, going clockwise. I started on the left of the 5-volt DC source. The first thing we hit is a minus sign, so it's minus 5 volts DC. Plus R1, the first thing we hit there was a plus sign, so plus R1 times I2, plus R2 times I2 once again as we continue clockwise. And then we run into R3 again, so pay particular attention to this. From the perspective of loop 2, our I2 current encounters R3 with a plus symbol. That's the first thing we do on the right side of the circuit. We're in mesh 2 now. Now what's going against us is the loop current I1. So the voltage drop across R3 from the perspective of mesh 2 is going to be R3 times I2 minus I1. So pay particular attention to that. So we've simplified both loop equations, and the next thing we're doing is solving those 2 equations. And you can solve them in whichever way you're most comfortable with. Personally, I like to do substitution. So let me write out these loop equations once again. We have 135 I1 minus 100 I2 is equal to 10. And the loop equation for loop 2 is going to be minus 100 I1 plus 225 I2 is equal to 5. So once again, we have 2 equations and 2 unknowns. And what I'm going to do is just simply plug one equation into the other. So solving for I1, we get 135. I1 is equal to 10 plus 100 I2. And I1 is simply equal to 10 plus 100 I2 over 135. So we can plug that loop 1 equation into loop 2, and we can solve for I2. So that's what we're going to do now. So at this point, there really isn't too much more to explain. We're just going to solve for I2 by substitution now, which isn't too difficult, just a little bit of algebra. So we get 151 I2 is equal to 12.4. And simply dividing 12.4 by 151 gives us 82.1 milliamps. And this value for I2 can be used to solve for the current in the first mesh. Now, it's always a good idea to determine whether your answers make sense. Do the answers make sense? Is there a quick way to check? And yes, we can check simply by applying the Kirchoff's voltage law. Do the voltage drops in each loop add up to 0? So let's find out. Here in the first loop, we have 1.34 volts plus 5.29 plus 3.38. Does it equal 10? And it's roughly 10. It's about 10.01. So it's close enough. If we had decided to use less rounding and add more decimal places to our calculations, it would have been that much closer to 10 volts. The same thing for loop 2. So here we have about 4.975. It's approximately equal to 5. So our answers are pretty close. What I've done also is run a piece-by simulation, and we can pretty much see how close we got. And we got pretty close. PSpice likes to determine voltages with respect to ground, so the voltages look like they're off, but if you add them up at each point, you will see they are correct. The current through each loop is, we have 135 milliamps on loop 1 and 82.21 milliamps on loop 2. So we were pretty close with this analysis. So thanks for watching. I will be adding more problems in the coming days and weeks. I hope to make this more of an extended video series with more challenging problems, and I hope that helps. Thank you.